I've gotten the request to explain how I approach multivariate modeling using JMP. Before we get started talking about the multivariate modeling, there are a few statistical terms that I wish to clarify before going onwards. Now, these are terms that help us define what are we looking for in multivariate modeling, and how do we determine whether something gets to, let's say, survive in our final model. Okay, so as an example, today I've brought this data set. It's a data set of a moving company, and they're trying to explain how long time it takes to move a certain amount of. So I have hours as my what I'm trying to explain, like the quality parameter. I have how many cubic meters there's to move, how many large furniture to move, and whether or not I have an elevator. And I like this data set because it's very simple to understand, and we both have some continuous factors and also a categorical factor of 2 levels. So there's 3 things we're looking for in multivariate modeling. So let's talk about them. The first thing are main effects. So if we make a graph folder, we take a single factor and plot that by meter. And we see we maybe make that into a regression line. We're going to make today's first predictive model by pressing equation. And here we have a very simple predictive model. We have that hours is equal to minus 2.3 plus almost 2 for every meter of stuff we have to move. There's one effect in this model, and that effect is called meter, and that is a main effect. So how many main effects do we have in our data? Well, we have 3 main effects, and all of these is something that we want to look at whether or not they are significant. To test whether things are significant individually, as we did with linear, like single x's and single y's, we're going to use the platform that's called fit model, or fit y by x. Because in this model we can say, well, hours is the response, and these 3 are our factors. But doing it like this, we'll have them side by side in this manner. And in here we can, of course, let's try and see how that will look. I'm holding down Control and then clicking on the bivariate fit of hours of the meter, and I'm fitting a line. That will fit a line to these 2 because they have the same format. It's continuous by continuous plot. They're both bivariate. I can see down here that these are in fact significant. And what that means, or down here, what that means is yes, there is a correlation between meter and hours. How much I have to move compared to the time it takes to move it. There's also a positive correlation to how many large furniture they have to how long time it takes to move it. So that's how we individually search for whether or not we have this linear effect between large and meter and my response hours. Let's try and look at another kind of effect, which is elevator, which is a yes/no response. So here we can do like a means ANOVA, and we can see in this case, yes, this elevator is in fact also a significant effect. Now I've built 3 different models. So I have a model for hours and meter, hours and large, and hours and elevator. But that is not what I'm trying to achieve. I want one single model where I will combine all of these information. So I want JMP to not do it the way we're doing it right now, but combining all of this information. So, and just before we do that, there's one more thing I want us to consider. Is there anything else we could be adding to this model? And yes, there are. But what other things do we have in modeling than main effects? Well, we have what we call curvature effects. So right now I'm forcing a straight line onto this fit between meter and hours. And if we look at that fit in the graph builder plot we made just before, we can look at, let's look at what's called the RMSE. So the root mean square error is how wrong this model is. It's how good a fit do I have right now. And what it says, it's the same It's in the same unit as what we're trying to explain, so it's in hours. So how wrong am I? Well, I'm 5 hours wrong, and I'm unhappy with that error. That's too high. Well, that says that if I'm trying to move 20 feet or 20 meters cubic, that's going to take 37 hours. But I'm 5 hours wrong on that estimation, and I want to reduce that number. And what we do to reduce that number is adding more variables, but also adding whether these could be quadratic fits instead. So now you can see I've changed this equation that I had over here. I've added a new effect, and this is not a main effect, it's a quadratic effect, because I'm searching for whether or not I could explain this with a curve. To see whether this effect is significant, I can't see that in here, but I can see that the RMSE was improved by half an hour, so that's a good thing. But if we go back to the fit group over here where we have hours and meter, we can try and instead of fitting the line, we can try and fit a polynomial, to quadratic. And now we got this green line as well, and you can see down here I have two fits. I have the linear fit and the polynomial fit. If I open the polynomial fit, what I did before is that I hold down Control, and that will then close all the subgroups. And I think that's just nice because it just makes it easier for us to see what we have open at the moment. So I'm opening the polynomial fit and seeing down here that meter is in fact significant. It has a p-value lower than 0.05, and the meter to the power of 2 is also significant. So that's a term we might want to add on a later stage. So that's two things. What's the last thing that we will want to add to models for explanation? Well, that's interaction between factors, an interaction between meter, lodge, and elevator. So more than just meter having an effect on hours, meter might have an effect on elevator. Now that's difficult to explain right now, but let me show how that looks by an example, and we can try and look at it there. Okay. So now we're going to exit the realm of linear modeling and enter the realm of multivariate modeling. And to do that, we need to change platform again and go into the fit model. To build what's called a main effect model, what we do is we add hours as what we're trying to explain. We add our three terms to the model effects, and now I press run. I also changed this emphasis to effect screening, and that just detects what is going to be available on the next screen. I just like this one the most. I mean, I could start with a minimal and build that onto an effect screening, or I could start with the effect leverage and have that look as an effect screening. But this is just the one I like the most. Okay, I'm just going to keep this open and say run. Now we have a main effect model. Close some of these down. And we can see here, well, in fact, all of these three are significant. It's no surprise, they were significant before as well. But combining these three into one model, you can see that the RMSE is now 3. So we've 2 hours better than just having one effect, now that we have 3 effects. And one thing that could be interesting, if I can find it quickly, let's see, is the prediction expression. And the prediction expression is, again, what we discussed in the graph filter, that before we just had this expression. But now I've added, so now we're starting at minus 0.4. Then we're adding 1 for every meter. We're adding 5 hours for every large furniture. And we have this matched effect. Well, what this means is that if there is an elevator, yes, then we got to subtract 3.4 from the output. And if there is not an elevator, we're going to add 3. So the effect of an elevator is like 6.6, 6.7 hours. So this is the same equation as there's always been. We're just trying, so the amount of hours is equal to this expression. And it's nice because it just shows that this is not a black box approach. It's a very understandable approach when we take it slowly like this. Now this equation becomes larger and larger, determined by the amount of effects we have up here. So now we have 3 here. We have large, meter, and elevator. And in turn, we also have large, meter, and elevator down here. So adding effects to the model we'll continue growing our expression. Okay. Down here we have the profiler, and we can then see how these effects are affecting our output. Okay, let's try and add some more. Now what we could do is we could say, well, we knew that meter and meter crossed wasn't a significant effect. So here we have meter times meter, and if we run this, you can now see that I have another. Before we had 3, now I have 4. And yes, that is a significant term, and that improved the IMSE further down. But this becomes a really manual process, so that's too time consuming when we want to look at all the possible things we can and then remove all the ones that are insignificant. Okay, so to do that, what we do is that you have to highlight all the factors, and then let's just make sure that this is cleared. You then highlight factors, and you add them by saying macro response surface. Now, I'm going to do that one more time for us to make sure that we saw the process of that. So the process of adding everything that might be relevant to look at down here is to select them in their column list, press the macro, and then press the response surface. Now the response surface will give us the main effects. So I have meter, large, and elevator. It will give us curvature where they are relevant. So I can't have the curvature for elevator because it's a yes-no response, so that doesn't make sense. And I then have 3 new things that we hadn't had before. So that's meter and large, meter and elevator, and large and elevator. So those are the 3 interaction terms, because I want to see how these different ones are affecting each other. Okay, so pressing run now, we for the first time see something new. And that is that not all of these are significant. Like not all of these have a p-value below 0.05. So that's like the rule of thumb we're going for. That's not a magic number, but it's the rule of thumb of whether something should survive in our model. So what we're going to just about to do is called backward elimination. And what we do, we have to select a factor and then press remove because the p-value is too high. And see how okay, just going to do that again. Run. See how that affects the other p-value. So when I press remove this, all of a sudden this meter is now the other one, but before it was large and elevator. And the reason for that is that all of these p-values are highly dependent on the number of samples I have available. So as we reduce this factor list, this p-value calculations are changed. And we're going to come back to why that's an important deal. So this is 9, I'm going to remove that. This is 18, I'm going to remove that as well. This is 8. I'm going to keep that because I want us to explain like what is this large times elevator effect that we have right there. So now I have large 3 times in my model. I have large as a main effect, I have large as a curvature effect, and I have large as an interaction between large and elevator. Okay, let's try and go down and look at the profiler. So the difference between before and now is that I have also looking at the expression. You can see it becomes even more complicated, but it's because now I have 5 terms here, and I will in turn have 1, 2, 3, 4, 5 terms in my model. So I have the 3 main effects, I have the large multiplied by large, so that's the curvature effect, and I have the large multiplied by elevator, which is then my interaction between large and elevator. Okay. Down here we have the new thing that we didn't have before is now there's a slight curve to how large is affecting. It's not a very dramatic curve, but it means that the more pianos people have in their apartment, the worse it will get. Like it's not just a linear effect, it actually becomes worse and worse. But the other effect, which is more interesting, is this large and elevator effect. Here we can see that if there's just one big furniture, the effect of having that elevator becomes from 20 to 23. So it's about a 3-hour difference on having an elevator. Now you might remember from before, that the effect, when we just had the main effect model, was 6 hours. So all of a sudden it's 3 instead of 6. And that's because now we have this interaction term saying, well, actually, this elevator effect is a function also of how many pianos people have. So you see, when I dial up to 7 pianos, notice how the slope between yes and no becomes larger. Now there's a small slope, and now there's a large slope. And this is visually what an interaction does to a model. It means that the effect of one of your factors is dependent on another factor. So now if people have 7 pianos, there better be an elevator, because the difference is now 11 hours. It's from 50 to 61, or almost 62, so almost 12 hours. So the effect when we have a high amount of pianos is 4 times as big than we just have small pianos. And we can mechanistically understand this interaction as well. Like if this is the 7th couch we're carrying downstairs, there better be an elevator to take these couches down. Okay. Now, last subject for the video. What we've been doing now, like eliminating terms from our model, is called backward elimination, because we enter everything into the model and remove them backwards from the bottom. Let's say remove, and we stop when we get to a p-value of 5. So that's there, fine. There's other ways of approaching this. There's something that's called forward elimination. There's other things to, instead of using p-values, we can use other things than other criteria for removal. And to access all of that, we need to go into, like, let's close this one. Instead of doing personality standard least squares, we need to change this to stepwise. And that will then run, that will open this platform instead. Now, here is the list, the entire list of things that can enter my model. Not, as we've seen before, not all of these are significant. Every time something is checkmarked, that effect is entering the model. So what I want Jump to do is select which of these are significant for me. So now I have the stopping rules as the BIC. We can have it, so the p-value threshold is the classical one we've been using so far. But there, as I said earlier, there's other ways for determining. Let's use the BIC, that's the Bayesian criteria. You can read about those criteria on our website if you are so inclined. So I'm just going to use the like the standard settings and press go. And notice how I then have 5 check marks and 3 empty boxes. Meaning when I then press make model, Jump has already removed some of the effect. And I can go to effect screening, say run, and see how all of these effects are now significant. And then you can say, well, this is strange because we only had 4 effects that was significant before, but now all of a sudden we have 3 effects, or 5 effects which are significant. And that's because when we do backward elimination, we are, as I said earlier, the p-values are dependent on the amount of effects you have in your model. So because we're doing backward elimination, the very first one we remove might have been significant in another combination of these. So when we're doing the elimination in different directions, some of the terms that proved insignificant in one method might be significant in the other method. So this is actually also a way for us to determine significance in some of these many factors. So that's how this stepwise works. It's, for me, the most efficient way of building a lot of different models. Let's do it one more time. So what I do is I go to Analyze, Fit Model. I select what I'm trying to explain in the Y, so I do hours to the Y. Down here I say, okay, well, I want these 3 effects. I go macro, response surface. I change personality to stepwise and say run. You can play with the stopping rules. I'll encourage you just to try different things. There's also different options available here. Now we can maybe talk about this in another video if that's important. What I do is I just try stuff, see if that changes the output of the model, and then see for future measurements which of these models are performing the best. But then I say go. do the selection. I say make model. I say effect screening and run. And I then look whether some of these are higher than 5, and they're not. And I'm happy with the model. Okay, let's try and do that quickly with another more advanced example, just so you to see that this actually works also on larger data sets. So I have here a definitive screening design from, let's do this like so. So here I have a data set that has 10 factors, and it has 21 data rows. So using the process that we just discussed, what we do is we go to Analyze, Fit Model. I take yield is what we're trying to explain. These are my 10 factors. I add them as a response surface. And you see how this list becomes very long. And I mean, doing this manually would be tiresome. So this changing personality to Stepwise is a really good method. We say run. And I just go ahead and press go. JMP will then identify some of these as significant, but notice how many of these are not significant. So I've really removed a lot of terms from my model. I then go and say make model and change this emphasis to effect screening. No, it was already. Okay. Then I say run. And now I can see all of these have proven to be significant. That's a lot of effects. Well, we can then look at this saying, well, yes, it's significant, but it's not very interesting. It's very flat, some of these effects. The really big one is monomer, and of course temperature, and to some degree also water. Thanks for listening. I hope this was helpful. I hope that you can use this approach. I'll just do it one more time to see. It was analyze, fit model, select the quality aspect, put it into Y, select your factors, add them as a response surface, change personality to Stepwise, run, press go, see the magic work, make model, effect screening, press run, and maybe you need to do some additional removal here. If you have any questions, we have the community as well. I hope this was helpful, and talk to you soon.